Right, in this video, we're going to talk about functions and representing them as equations. So another good way uh, to represent a function, f of x, so is with an equation or an algebraic equation. So something like this. Um, Now you know how to graph this, so we could think about the function also represented as a graph. So the equation x squared plus 1 you should recognize as a parabola with a y-intercept of 1, so it's been sort of shifted up 1, we usually say. And then it would just be opening up. So that curve is the function, and it's represented by this equation. So it's another way to represent a function sort of with infinite number of points. You might say, okay, well, now you can answer questions like, what is f at 2? Well, you could go to the graph and sort of go over to 2 and figure out sort of what the f at, maybe I should label the axes x and f at x and sort of label them. Or you could just substitute it into the algebraic equation. Right, so f at 2 means that, remember, this is your input x, so wherever you see an x, you're going to write a 2. And you just substitute that right into the equation. So we have 4 plus 1 plus 5. So therefore, f at 2 is equal to 5. And you could do this for any value in the domain of f. And the good thing is now we don't need to use the graph. You can be more accurate using the equation than you would with the graph. Another question you might want to know is, well, what's the domain of f? We don't have that notation, so maybe I'll just write it. So what is domain of f? Now here you have to think about like what you know. You have to think about the graph. You have to think about what you know about this equation. So basically the domain, unless we restrict it or say otherwise, will be any value which works for this equation. So what numbers are we allowed to square and add 1 to? Well, really any number you can square and add 1 to. So in this case, the domain is all real numbers. So that's indicated by these arrows, right? These arrows indicate we keep going forever. So you'll always keep going along the x, and always keep going along the x that way. So in this case, the domain, and I'm going to introduce a notation here. The notation, and this is sort of notation I use. You'll see it sometimes. It's not common. It's not necessarily common. It's not used in our textbook. It's not used in a lot of textbooks, but I like it. So the domain of f is the set. So instead of saying, let A be the domain of f, I'm just going to use this notation, domain f is equal to x such that x is a real number. So all real numbers. So let's look at another example. Well, that was an example we're familiar with. Another algebraic equation. So let's consider this function g at x. So you don't always have to use f, right? You can use different letters. G, h is common. It doesn't really matter. F is the most common. G, sometimes h we use for function. You'll see other letters, but usually we don't use like x because, well, then you'd have x of x, and that would be not good. So what's the domain of this? So what is domain of g? So the domain of g, well, if you knew what the graph looked like, this is a square root function. So a square root function normally looks like that, and then the plus 1 means it shifted 1 to the left. If you don't remember that, we'll talk more about transformations of functions later. So it looks like that. This is the value -1. So you might be able to see from this that x is always bigger than -1, bigger than or equal to. Or you might, just think about what this function, how you could evaluate this function. So we know that square root functions, you can only take the square root of positive numbers. So we know that whatever is under the square root, x plus 1, must be bigger than or equal to 0. Otherwise, you couldn't take the square root of that number. So which values of x is that true for? Well, you can now let me write it this way. If you solve this just like you would an equation, right? If you subtract 1 from sort of both sides, the 1 and the negative 1 would cancel. You'd have x bigger than or equal to 0 minus 1 would be negative 1. So that means x must be bigger than or equal to negative 1, which is what we see over in this graph. So therefore, the domain of G is equal to the set of all x such that x is bigger than or equal to negative 1. And then if you want, you can end it there. Sometimes, notice I didn't write that x is a real number. If you don't write that, it's assumed that that's the case. It will assume it's the case. It's, when you do calculus and in this course too, advanced functions, we're normally dealing with real numbers. So if it's not written, it's sort of assumed, unless you're doing other types of math where you deal with different types of numbers. Another question you might say, well, what about the range? So what is the range? And the range can be a little bit trickier to figure out. So for right now, the way we're going to determine the range is basically by looking at the graph. So we see that the smallest value of the range, so the range is which dependent variable is taken on. So our smallest sort of f at x value is right on the axis here, so it's 0. And then this arrow indicates we keep going up. So basically, the range is, so the range, I don't have any other notation for range, so we're just going to write it as a set. So y such that y is bigger than or equal to 0. And the way we get that is just by looking at this graph up here. It's sometimes harder to figure out algebraically, but we'll do examples of stuff like that later on. Okay. So that is how we can. These are some examples of functions written as equations. So it's often helpful to think about what the graph of that equation looks like, but if you don't want to graph it, or if you don't need to, or if you don't know what the graph looks like, sometimes you can just look at the equation and figure out things like the domain. It's also good, remember up here, for evaluating specific values just by using the equation. You don't have to go to the graph all the time to find the values.